So now I switch to English, and today's topic is ordinary differential equations solving. First, we'll consider a simple example from where we can obtain a system of ordinary differential equation in normalized form. Are you familiar with this terminology, normalized form of ordinary differential equations?
Yes, it's about coefficients.
Coefficients before what?
Or functions.
Okay, we'll talk about that anyway. So, and as a simple example from where we can obtain a problem with differential equations, let me first name the chapter. Chapter is numerical solution of Cauchy's problem for ODE. And you told me that you have already heard something on this topic, right? Numerical solution of ordinary differential equations. But still, we will briefly review this whole area. I will not go into every detail, but I want to review the most important topics. Probably there are some gaps that you still have, and this might be useful anyway. So paragraph number 1 is introduction. Introductory example. Let's say introductory example. So let us consider a problem. We have a car is moving along the road, and there is a bump on the road. So let's say this is a bump with a pretty large radius. This letter R will not be involved in any formula, so this is just for illustration. So what we want to know about this car? We want to know how hard will be the feeling of this bump for the driver. So what the driver will feel when the car approaches and goes through this bump. What does it mean mechanically, from a mechanical point of view? Every car has a suspension system. Let's consider this suspension system in enlarged form. So we have a spring and a damper. And if we reformulate this real-life problem into mechanical problem, what we are interested in is the displacement of this point C, which is stiffly attached to the top of the suspension system. And we have a point A, which is stiffly attached to the wheel, and let's assume that the wheel itself is also stiff. So we don't account for any additional elasticity of the rubber or anything else, just to simplify our problem. Because if we want to account for this, it's going to involve another system like this, like the suspension system. It will also involve a spring. The model of this real wheel will also involve spring and a damper. So we can just combine those. So let's assume this is stiff, and let us assume that we know the form of this bump on the road. The form of this bump is described with this formula. So L capital is the length of the bump, h is its maximum height, what else? X is just our coordinate along the road. What else do we know? So we definitely know H, we know L. What else we need? We know gravity. And we should also know the original length of the spring in its free form, without any compression or tension. And we should be aware of the mass associated with this part of the car. Let us divide the car into two halves for simplicity. Let us not consider the back suspension system and its actual collaboration with the front suspension system. Let us consider only one part. So with these assumptions, I think we can write, or you can write, the force balance. What is the force balance at point C? What forces are acting on point C?
So it's force from the
Spring.
Spring, yeah,
So,
from spring.
Elasticity force,
Yes.
elastic force, right? Is directed upwards. Do you agree? Upwards.
Yeah.
Or it may be directed downwards if the spring is in tension.
Yeah, but our case.
Well, it will be oscillating. As we approach the bump, it will first compress and then it will go back, and at some point it will be in tension. So this force will change its direction. It's an oscillatory movement. Then, what other forces are acting on point C with associated mass m?
Yeah, gravity.
Gravity force, which is what? mg, right? Oh, I should be using consistent notation for the vectors. What else? Something else is associated with this element. This is usually, technically, it is implemented as an oil bath, where a piston is moving in some can. So this oil is dissipating energy. So it prevents the spring from jumping up and down infinitely. So it dissipates energy, so the spring stops pretty quickly, stops its oscillation. So what is the action if we have compressed our spring and we have elastic force directed upwards? So what will be the direction of this force? Friction force. Friction force. Friction comes from here. Okay, and this seems to be all the forces that we have, right? How can we write the law defining the movement of the point C? Say, I want to know the position of this point C, UC, along some axis. I need an axis. What I wanted to name this axis. Well, actually, at this point, I don't need to think about access. So,
So we can find it through potential energy.
I suggest a simpler approach, just using a second law, the second Newton's law. So let us say that the velocity is what? This position, or the change of position divided by time, well, actually time derivative of it. And the acceleration is the second derivative. Right? So in Newton's law, the acceleration must be multiplied by the mass of the object. And to the right of it, we have to account for all the forces that are acting, projecting them to one axis. Let's do that. So F elastic with plus, let's say this axis, let's call it Y, is directed upwards. Elastic, okay, elastic, minus friction force, minus the friction force, and minus the gravity force. You agree? Okay, so what's next? How to calculate this elastic force? We need to know also some other information about the spring, and let's call this information K small. It will be the elasticity coefficient. Let's say that it is linear elastic what? Object, so to say, construction. So it obeys the linear elasticity or Hooke's law, which means that this force is equal to K multiplied by the change of the length of the spring, right? So if the original length is L, then we have to do what? We have to subtract this shift of the point C from this shift in point C, the shift of the point A. Am I correct? So we want to calculate this distance, this new distance.
Yes.
After deformation. This new distance, let's name it L tilde.
So we just need to K multiply OA plus O.
Could you say it again?
Minus.
Say it again?
Because maybe I'm mistaken, but elasticity force is K multiplied minus K multiplied by delta A.
Minus K multiplied by the delta L. Okay, let's take your expression. Minus K multiplied by delta L, and our goal is to calculate this delta L correctly.
Yes.
Let's or express this delta L through the other quantities we have. You're right, yes, you're right. If the delta L
Okay.
is positive,
Yes.
then this formula is true. If you are if you are making your spring longer, delta L is positive when you are making your spring longer.
It's negative. Short is
Do you want this delta L to be negative when you are making your spring longer?
no.
Okay.
So it is that.
Let's continue. So, how to calculate it so that we get the right sign afterwards? So we have a movement of point A together with the road, right? So actually this UA is just U capital of X, that we know. Okay, this is prescribed. And we have an unknown position of UC during the deformation. So we have to subtract from UC this UA to get the new length, right? This will be the new length. Do you agree? UC minus UA will be the L tilde. Let's take 0 here.
Okay.
If this point has moved to the maximum ux, u capital max position, let's imagine that this point A has moved to the maximum possible position of this bump to the top point. This is the distance h actually. What happened to this point, to C? It has moved somewhere at some position which is defined by the elasticity of our spring and the friction properties of our damper. Okay? How to find out the distance between the point C and point A in new position? What will be the distance? I'm saying this is nu UC minus mu UA.
I thought that UC and UA, as you said before, it's just a shift. And this is not its coordinates. Okay, I guess.
Let's assume that these are the coordinates for simplicity, okay? So I introduced this coordinate axis, vertical coordinate axis. I'm not explaining clear enough. So, so would you agree with this expression then?
Yes.
Okay. Okay. But I have a problem because I have an extra minus here. So I don't like the minus that I have. Which doesn't coincide with my expressions in my notes for some reason.
No, in this, as you should delete the minus in the second expression.
Why?
Before the equal sign. Because it just contains in L minus.
Yes, that's what I was saying before. So this minus would be valid if we had minus here in this parenthesis.
Yeah.
So, sorry guys who will be watching video. We are changing things on the board, but now this is correct. This expression is correct. And finally we have the complete formula like this. For the elasticity force. Let's talk about friction. What is the friction force? Well, friction force is proportional to some viscosity coefficient of the damper multiplied by what? By the velocity. Usually the friction force that comes from the liquid viscous movement through some liquid at small speeds, when the speed is not very high, it is proportional to the velocity of this movement. I think this is discussed even in the school physics course. What point should we take here? It's gonna be, actually it's gonna be the difference again between point C and point A. This is our L tilde. By dt, so derivative of that. Okay, and mg is mg, we have nothing to do with that. So how we should simplify or treat these expressions? So first of all, we have to appreciate that we know UA. And here, so we can move everything we know to the right hand side and everything we don't know to the left hand side of this equation. Let's do that. M d2u by dt squared, so to say, which is not correct, is equal to plus k uc. I should be writing c here. C. What else? Help me. Plus duc dt. And that's it for the left hand side, right? And in the right hand side we have k by L plus k by UA. What else? Plus or minus? Plus b dua by t. Anything else? Yes, mg. Is it correct now? Seems to be correct. This guy we know, and this guy we can calculate, right? From this formula. So, do you want me to take derivatives here, or you can just believe me that we can calculate that? Okay, well, let's do this as a homework for anyone who wants. So, and what we get? We have obtained an ordinary differential equation. This is an ordinary differential equation of second order. To find an unknown function u c of time, right? So if we want to know the law which this u c obeys, we have to solve this ordinary differential equation. But from the theory of ordinary differential equations that someone might have had as a part of mathematics classes or some other courses, it is known that this equation defines an infinite number of different curves uc of t. So there is an infinite number of solutions to this equation. And what we have to do to select only one solution from this set of possible solutions.
Yeah, we need initial conditions.
We need initial conditions. So, well, maybe I need to represent this idea graphically. So, let's have time here and say that this is uc of t. So, let's assume that this moment from t0 to t corresponds to the location of our bump. So t0 is the moment of time when the car wheel approaches this point, and t capital is the moment of time when the car wheel approaches this point, the end of the bump. Right? Then for the uc we can imagine that we might have this kind of solution. or maybe something more complex because of the spring, right? And this equation defines all the family of the solutions of this kind. The whole family. Infinite, upwards and downwards. And we need to select only one curve which corresponds to our particular case. And how do we define this case? First idea is that we have to fix this uc of t0. So we have to say what was the state of this point, what was the coordinate of this point as the car has approached this point t0 at t0, right? So let's say that we know the initial location of C, vertical location of C, and call it u0. This is the first condition, but it's not enough. Probably this is not clear from the picture that it's not enough, but we need to also define the angle at which this one of these curves starts from point t0. Let's put t0 here, it's better. Okay, not only the location, not only the position of point C, but also the velocity at which this point C is already moving, or might be already moving. duc by t at time t0 is equal to something v0. So if we define this equation plus these boundary conditions, we would be able to select a unique solution. For our particular problem, let's assume these two quantities are just zeros. So we are coming close to the topic of to the topic we are considering, actually, numerical solution of Cauchy's problem. So this is already a Cauchy's problem, but for the second order ordinary differential equation. How to obtain a first order equation from this formulation? Are you aware of a technique?
Yeah, we just can change, make a parameter, what will be the first derivative.
Okay,
If not
great.
explicitly.
Great. Let's do that and obtain what we are going to obtain. One equation or something else?
If we include this parameter, so it will be the system.
A system. Okay, let's parameterize it. So let's let's introduce another function, z1 of t, which by definition will be equal to our uc of t. And another function, z2 of t, which by definition is equal to what? To the derivative of dz of t, which is equal to duc of t by t. So this is our trick. And after that, we are going to have a system of ordinary differential equations, of two ordinary differential equations, z2, because the derivative of this guy is just z2, and the derivative of this guy is what? Is everything, so this guy that we just defined is this term. So we have to move everything else to the right. Right, so it's going to be 1 divided by m minus k z1 minus minus bz2, this is z2, this is z1, plus kl plus kua, which is known, plus b dua by t, which is known, minus mg, which is known as well. This is how we obtained a normalized system of ordinary differential equations. And in order to make the solution unique, we have to translate these two initial conditions to our new notation. What is going to be? z1 of t0 is equal to u0, and z2 of t0 is equal to v0. And this system of differential equations, together with this set of initial conditions, are named a Cauchy's problem. For a system of ordinary differential equations of first order. Okay. It is just an example of how such system can be derived from a real physical problem. Okay, let's delete everything here. Maybe I had to do another step with a small step towards generalization. So I can combine these two functions into a vector, right? And I can say that this vector is called simply z. So z is a vector now, not a scalar quantity. And I can also combine everything at the right to the vector. I have deleted the formula, I'm sorry for that, but I can try to write a few terms to explain my idea. So not UC, but Z1, Z2, plus anything else that appeared here. So I can construct another vector from the right-hand sides, and I can say now that I'm solving a vector ordinary differential equation like this, right? So, and I can do the same thing with the initial conditions. Say it's gonna be a vector form of the system. I will not write on the board all the rest of the words that come together with this vector form of the system of ordinary differential equations in normalized form. So, as you can see, this vector, well, it depends on time, and it depends on the solution itself, the solution vector itself, right? The right-hand side. So this can be considered, well, this is very similar to the scalar equation, because the only difference is this understanding that z is a vector. So, starting from this formulation, or formulation very similar to this, we will talk about numerical solution of scalar scalar ordinary differential equations, having in mind that it's very easy to translate all the methods to the vector case. Almost everything will be translated directly. Only the justification and error estimations and stability estimations will have to be modified to account for the systems of equations, not one equation. But the formulations of the methods themselves is exactly the same. And you will face a problem, or not a problem, but the need to modify something in your program if you want to account for a system rather than one equation. Okay, so I will not go into generalization of these ideas that we just considered, because I hope everything is clear anyway. And my question is, do we need a break today? How do you feel? At 11 or later or earlier?
Maybe a short break.
Now or later?
We can make it now.
Okay, let's make a short break, like 10 minutes maybe.